Mindsetters, grade 11s, it's finally your time to shine. I don't know why I'm doing this, but anyway, you're hanging out with Looney and Phil. How are you, Phil?
I'm great, thanks, and you, Looney?
I'm good, thank you. What are we doing for the Mindsetters today?
Well, today we're continuing from last week. We are talking a little bit more about redox reactions.
Okay, cool.
Yeah.
Mindsetters, you heard it, grade 11's redox reactions. But before we get into the lesson, as you all know, we've got this beautiful Samsung device right here. It's a Samsung tablet, guys. I just want to show you that we do have new content on our Learning Hub. So if you do have a Samsung premium smartphone or a Samsung tablet, you can access this Learning Hub on your gadget. Guys, it's very great to get all the awesome Learn Extra exam revision for you guys to prepare yourselves for the exams. But don't sweat if you don't have a Samsung device, because we do have a Learn Extra exam revision marathon competition running. So all you need to do is that you need to download your notes, and then right at the bottom of the notes, the last page, because I need to do this slowly because you guys don't understand. The last page at the bottom, there is a race number. What you do with that race number is that I will post a link with the entry form on our Facebook page. What you do with that entry form is that you fill in all your information and the race number, and then you'll stand yourself a chance to be entered into a lucky draw. And then you must watch all the live shows, because we won't tell you when we'll be announcing winners and all of that stuff. Must make sure you're always watching, because it can happen at any time. But make sure you ask your grandmother, your father, everyone to enter, guys. But you must remember, you must only enter once to stand a chance to win one of 9 awesome Samsung tablets. So it's as simple as that. Okay, guys? Remember to hit me up on Facebook, facebook.com/LearnExtra, Twitter @LearnExtra, LearnExtraLive.co.za is where you get your notes, your videos, your schedules, and everything else. And then Phil will now give you the lesson.
Well, guys, last week we started talking about reduction and oxidation. I hope that you were following very, very carefully. If not, don't worry too much. There's going to be a little bit of revision packed into today. We're going to be dealing with some reduction, some oxidation, as I said before. Okay, so guys, get onto Facebook, start talking about this, guys, that this is a section that shouldn't be feared. This is a section which can be conquered as long as we pay attention to some of the details. Okay, so let's just start talking about reduction and oxidation again, and let's pay attention to the bits and pieces which go into there. Okay, so if you were watching last week, we took apart this word, reduction and oxidation. So redox was the name of the game. So split into those two parts, reduction and oxidation. Now this is part 2 that we're dealing with, and we're going to carry on from last week. Now last week we placed a great emphasis on the actual meaning of the word reduction and oxidation, and then we started to come up with this idea about oxidation numbers. So what we're going to do now is we're going to revise that firstly. We're going to revise oxidation numbers, and we're going to give a little bit of a lead into how to do half reactions. Okay, now half reactions are something which really bother a lot of people, but they shouldn't. I'm going to show you a couple of tricks. We're going to work through some examples together. Guys, if you get online and get our notes and download the notes, that means that you can practice some of these examples with us. Okay, now I'm going to write some half reactions to show my reduction and oxidation. So guys, we're going to represent reduction and oxidation separately. That's the name of tonight's game. And then, here comes the magic part. This is where we put it all together. We're going to combine the half reactions, so put them back together to make a whole reaction, which I call a net-ionic reaction. And that's where a lot of people really get sort of tongue-tied, and they get stuck and they're not sure where to go. There's some steps to follow, guys. Really not too difficult. Okay, so now, as I said, we need to revise what oxidation numbers are, the meaning behind reduction and oxidation. So what I'm going to do is I'm going to use one of the examples that we used last week. And to illustrate this point, I wanted to start dealing with reduction and oxidation numbers again. Okay, now, the definition which we gave you last week is that oxidation numbers tell us the number of electrons which have been removed. Okay, so guys, let me just give you a little bit of a lead up to this. When you treat something with oxygen, oxygen is great at taking electrons. So I call this word oxidation the removal of electrons, because that's what oxygen would do. But now oxidation doesn't necessarily always mean that oxygen is involved. All that's involved when you do oxidation to something is that you're removing electrons. The oxidation number is how many electrons have been removed. Okay, So now, when would I start to remove electrons? Well, remember that some elements like to lose electrons. Okay, we'll deal with those in a minute. Okay, so just a reminder that oxidation definitely is the loss of electrons, and here's our example from last week. Okay, now when we made this formula MgO, okay, now the way that I make MgO, I take magnesium and I take oxygen and I'll combine those two atoms, but now there's an agreement between them. Magnesium is going to lose 2 electrons in this agreement. Why? Because magnesium has got its 2 valence electrons if you draw the Lewis dot diagram. So magnesium's got these 2 electrons which can be lost to oxygen. So let's just represent this with my Lewis dot diagrams, and let's show why 2 electrons get lost. Okay, so here's my Lewis dot diagram. Magnesium is going to lose 1, 2 electrons, and the product is going to be magnesium without 2 of its electrons that it had before. This means that the oxidation number of magnesium inside MgO is positive 2. So 2 electrons are missing. This is how I talk about the oxidation numbers, mostly of metals inside compounds. So let's just rewind for a second and make sure that we got that concept correctly. Okay, oxidation is the loss of electrons. The oxidation number is how many electrons have been lost. So MgO, we're going to concentrate on the magnesium. I know that that magnesium gave away those 2 electrons. Those 2 electrons went onto the oxygen. That meant that the oxidation number of magnesium was positive 2. Now last week, some of you had really great questions, and you asked me, what happens if an element gains electrons? What about the oxygen? Okay, so oxygen, each oxygen atom gains the 2 electrons. Okay, now you're saying, well, how do I represent the gain of 2 electrons if the oxidation number is how many I've lost? And the answer is, I use a negative oxidation number. So let's just make a little bit of space here and let's emphasize what's going on here. So I use a negative oxidation number. How many electrons are missing from oxygen? Negative 2. That means that it's got 2 extra electrons. So that means oxygen with 2 extra electrons. Now, if you've drawn out or represented the ion for oxygen, you'll know that the charge on oxygen is 2 negative. That means that it gained 2 electrons. Now, here's another reminder about how to assign oxidation numbers. That things from group 2, like magnesium, generally will have a positive 2 oxidation number when they're inside a compound. Oxygen generally will always be negative 2. Now, we're going to deal with a few examples a little bit later on and hopefully take some examples from you guys at home. So I want you to get on that Facebook page and share some of your problems with oxidation numbers, because if you don't know how to assign oxidation numbers, half reactions are really going to be horrible. Okay, so oxidation numbers really are not that difficult. So if you go through last week's notes, there's some rules inside there on how to assign these oxidation numbers. Guys, the notes are on the page. They are free to download. You can even go and watch last week's video online. That's how cool our website is. And what we're going to do is we're going to assign some oxidation numbers. Once you've got that down, we're going to write down some half reactions. Okay, so now let's go back to this example. Now, what are half reactions? Well, quite literally, they are half of the reaction. Now, you're going to tell the story from 2 different parts. I'm going to tell the story where something gains electrons, and I'm going to tell the story where something loses electrons. That is the reduction and the oxidation half reactions. The 2 half reactions are represented, if you remember from last week, by oil rig. Okay, now oil rig just seems like 2 little words that kind of scare me, and I'm not sure why I'm talking about oil rigs. This is oxidation and reduction chemistry. But if I remember from last week, oxidation is the loss of electrons, and this becomes very, very useful. So oxidation is loss, and if you can guess what RIG or RIG stands for, that means that reduction is the gain of electrons. So this is a very useful acronym when you're starting to deal with this. Oxidation is loss, which is oil. Reduction is gain, which is RIG. So this is a very nice thing. Most teachers will employ this. It's a really nice acronym to help me remember what's going on there. Okay, so now where are my 2 half reactions going to come from? One of my half reactions is going to tell the story of something which is losing electrons. The other half reaction is going to talk about the one which is going to gain electrons. Okay, now we've got to tell the story from those 2 parts, and we've got to keep in mind our oxidation numbers, or at least the charges, the story of each individual element. There's the story of the magnesium, and there's the story of the oxygen inside here. So we're going to tell the same story as a normal equation, but in two parts, one oxidation and one reduction. Now we're going to look at this example where I combine magnesium with oxygen to make MgO. You might say, how can I split this tiny reaction into two parts? Okay, well, first of all, I'm going to tell the story from the magnesium's point of view. I'm going to see what happened to the magnesium as it went from being a metal to being an ion. And the only way that I can do that is to pay attention to the oxidation number and the charge on magnesium. Okay, so the magnesium atom itself turned from an element on the left-hand side into an Mg2+ ion. So that's the first step, is to find out what happened to that particular part of your reaction. Sometimes I will call these things species, just the same way that you talk about different species of mammals and insects and plants. Okay, a species is just a type of redox term. I'm just saying that the magnesium is a species. So what happened to this species? Well, it changed from being neutral as an element to being +2 on the other side. So Mg turned into Mg2+. Now, that relied on my ability to see that I saw that Mg was a +2 oxidation number. It went from 0 to +2. It lost 2 electrons in the process. So what I'm going to do is I'm now going to write out the story of magnesium. Now you might say, okay, well, I start out with magnesium, and I end up as magnesium 2+. But now you might say, okay, what's going on over here? Now we've been naughty, we've skipped some steps. How do I arrive at this half reaction? I've written down the completed half reaction. So how do I begin this? How do I begin to write out my own half reaction? Okay, so let's start the story again. Let's write down what we do know. What happened to the magnesium? Let's tell the story of magnesium. So magnesium starts out as an element. Okay, we know this. Then, after the story had finished, I knew that magnesium had changed into Mg2+. Okay. But now, what about the electrons? Okay. Before we go any further, let's start drawing up some steps. The first step is to write down the two different species, Mg and Mg2+. The next step is to make sure that the atoms are balanced. One Mg atom, one Mg ion seems okay to me. Then, the third step is to balance out the charges using electrons. Okay, now here's the fundamental rule for these chemical equations. Chemical equations are not exactly the same as maths equations. You can't subtract things from these equations and have them still be correct. I'm sure you've noticed that you will never see something minus something in a chemical equation. So here's the correct way to do it. I noticed that on the left-hand side, the combined charges of everything, in other words, all of the oxidation numbers add up to 0. So I must find that on the right, they should still add up to 0. But there's a problem. I've got a 2 positive charge over there. The only way that you can balance out 2 positive charges is by putting 2 electrons, because each one has a negative charge. So let's just stop for a second. Step 1, I write out my two species, so magnesium became magnesium 2+. Then I balance the atoms. I balance the magnesium and the magnesium 2+. There's one of each, and that's okay. Now I'm going to balance the charges or the oxidation numbers. Okay, so on the left-hand side, I find a neutral atom, which adds up to 0. On the right-hand side, it should also add up to 0. The only way that you can get it to add up to 0 is if I cancel out that positive charge by adding 2 negatives, and that's where the 2 electrons come from. Now, here is another sign that we've done something correct. We know from our storytelling that electrons came off magnesium. Magnesium lost electrons. Now, if your electrons are written on the right-hand side, that means that electrons are being given out of my reaction. So electrons on the right means that oxidation is happening, and that's what happened to my magnesium. So let me just repeat that again. If the electrons are on the right, there's oxidation occurring. Electrons are being lost. Now, the thing that a lot of people get really confused about is that there's a positive over here. Positive, you're saying, okay, positive means add in maths. That means I'm adding electrons. No, guys. The positive over here means and. So let me tell that story again. Magnesium becomes a magnesium 2 plus and 2 electrons. That means that the 2 electrons came apart from my magnesium. I hope that you can see that. I'm going to give you guys a little bit of a challenge before we go away for an ad break. What I'm going to ask you is to write the story of oxygen. Now remember, magnesium underwent oxidation, so tell me about the reduction of oxygen. And I'm going to check the page and see if you guys can come up with the right answers. What do you think? It's time for a break, Lini?
Yep.
Okay.
Mindset is, it is time for a break, so don't go anywhere. Remember, Phil is asking you for a story about oxygen and that whole thing with what he's doing there. So make sure you do hit us up on Facebook with your answers. We will take a very short break, but don't go anywhere. We'll see you straight after this. Welcome back, Mindsetters, from that break. I hope you guys are still enjoying the show. Remember that, just to remind you guys, that from next week, Monday, which is the 14th of October, your lessons will start at 6 and end at 7. Yay, we're giving you a young upgrade there. We're taking you to the matric time slot. So grade 11s, from 6 till 7, you will have your time slot. Okay, your live shows will be from 6 till 7. We have exam revision coming up, so we trying to hook you guys up, you know, with the best of the best. So 6 till 7 is your time slot. So I hope you guys tune in. And then Phil, let's take this show on the road.
Absolutely. Okay, now before we went away for the ad break, okay, and we came back to some beautiful singing by Looney. Okay, now before we went away to the ad break, I was starting to talk about the story of magnesium, and magnesium was losing its 2 electrons. Magnesium was undergoing the loss of 2 electrons. Now, these 2 electrons show me how much the oxidation number of magnesium is. Magnesium had an oxidation number of 2 plus. That means that it's going to lose 2 electrons. Guys, there they are. You need to follow the electrons. You need to make sure that you know where the electrons are. And if they're on the right-hand side, that means that they've come out of the reaction. Now, I gave a little bit of a challenge, and it looks like you guys are trying. You're almost there. And we were asking you if you can tell the story of oxygen. Okay, so we're going to do the same thing for oxygen. And there it is, guys. There's the story of oxygen. We're almost all the way there. Now, oxygen's got a few more steps than magnesium. It's a little bit more complicated. Let's tell the story of oxygen. Okay, now I know that oxygen starts out as an element, which is O2. Oxygen as an element is diatomic, which is O2. Now, on the other side of this equation, I know that I've got to have an oxide ion, because it was oxygen inside a compound with a -2 oxidation number. So a -2 oxidation number means that I land up with a 2 negative charge. Now, there's many things wrong with this. I've got a long way to go. So that was step 1. Write down the 2 different forms of your element, the 2 different species, O2 and oxygen with a -2 ion. Okay, now I've got to balance my atoms, which is step 2. I know that there's 2 oxygens on the left. There must be 2 oxygens on the right. So step 2, I'm going to do in green here. I know that I have to have 2 oxygen atoms on either side. Doesn't matter about the charge, I need to balance out my atoms. I can't have 2 oxygens going in, and only one comes out with a -2 charge. That's impossible. You can't teleport atoms out of a chemical reaction. They need to come out if they went in. So here we go. 2 oxygen atoms went in, they were neutral. Now 2 oxygen atoms come out, and now they are -2 ions. So here's my last step, and let's switch colors again. So we're going to go now to purple, and I'm going to show you how to balance out the charge. Now on the left-hand side. Okay, so on the left-hand side there, I said, okay, well the left-hand side at the moment equals 0. But on the right-hand side, ooh, guys, look at this. I've got 2 oxide ions. Each one has a -2 charge, which makes a negative charge of 4. So the left-hand side, here's the problem, guys. You can't get rid of negative by using electrons. What you can do, though, is you can add negative to the other side. So I'm going to make both sides have a -4 charge. I want both of them to have a negative 4 charge. And the only way I can do that is by adding in 4 electrons. So 4 electrons go in, they add to oxygen, oxygen gains them, and this means that reduction is happening. So there we go, reduction is occurring. Now guys, if you weren't watching last week, I revised what the word reduction actually meant. Reduction meant that the oxidation number was going down. The oxidation number was being reduced. Let's prove it. Okay, so oxygen was happy on its own, it's diatomic, I breathe some in, or magnesium takes some in. If you were following closely last week, all elements have an oxidation number. So let's actually do this. O2 has an oxidation number of how much? It's 0, guys. It's an element. What happened to it? It went along to become a -2 ion. So that means that its oxidation number turned into -2. Guys, I don't know if you see what I see, but what I'm seeing is 0 goes down when it goes to -2. Guys, this is an indication that this is a reduction reaction. Okay, reduction is gain, you know oil rig, but here's another way to tell that reduction means the going down of my oxidation number. So what happened to oxygen? Oxygen turned into a -2 oxidation number. The number went down. Fantastic. And that's really great because we know that oxygen is undergoing reduction. Oxygen is not being oxidized. That doesn't make any sense. Magnesium was being oxidized because it's being treated with the oxygen. And that's great. So what I'm hoping we can do, and I think there were some questions online about this, weren't there?
Yes, about that.
Okay. All right. So guys, please keep posting. What I'm going to be doing is a little bit later on in the show, I'm actually going to ask for some of those questions. We're going to answer questions specifically about oxidation numbers and then how to turn them into half reactions. Are there some questions about this at the moment, or we're having to rifle through lots of these comments by the learners?
They gave what you're doing now, so they're on the...
Oh, fantastic.
Right.
This means that the guys are on the track and they're
Yes.
managing to get the correct half reactions.
Yes.
Guys, I want you to practice this, please, and that's exactly what we should do now. Okay, so what we're going to do is we're going to write down half reactions for these full reactions. We're going to tell the stories of each one of these elements. We're going to see what comes out on the other side. Okay. So now, what we're going to do for each one of these is we're going to tell the story of one element, then the second element. First, by following the steps, and then we're going to balance out the charges, and we're going to see what comes out. Okay, so now what I'm going to do is I'm going to color code this slightly. I'm going to follow the story of sodium as it goes from being an element to being inside a compound. Now, this relies on your oxidation numbers. Okay, so sodium. Sodium going into a compound requires a change in a charge because as an element, it's just Na. So let's identify the two parts. So Na becomes, and inside a compound with NaCl, it becomes Na+. So step 1 is complete. I've identified which parts. And guys, that's the hardest. I need to figure out what happened. I turned from an element into a metal ion. I turned into Na+. Okay, fantastic. Step 1 complete. Step 2, check to see if the atoms are balanced. 1 sodium, we're all good. Now what we've got to do is we've got to balance out the charges. Guys, let me give you a little bit of a tip. I can see that there's lots of pluses. Now, when you're trying to balance out pluses, put electrons on the same side as the pluses. If you're trying to balance out negatives, put the electrons on the other side. Remember that you can only add electrons. So let's do exactly that. So where would I put electrons to balance out the charges? On the left, there's a 0 charge. On the right, therefore, there must also be a 0 charge. So I'm going to add in 1 electron. So the right will also add up to 0. Now let's tell the story of Cl. Okay, so I'm going to do Cl in some green because chlorine is a nice green gas. So Cl changes from being chlorine as a gas, as an element, changing into a chloride ion. It's gone to make a compound with sodium. Remember that when elements go into compounds, there's usually redox that happens. This is one of the ways that you can spot if something is a redox reaction. Got something which was an element which is now inside a compound. And that is a sign that you're doing some redox. Now, chlorine definitely undergoes redox because chlorine loves its electrons. Chlorine wants to take electrons. So chlorine before the reaction was an element. So let's tell the story of chlorine. So chlorine was Cl2. Okay, after the reaction, I see Cl, which is inside a compound. Guys, Cl inside compounds, if you sign that oxidation number, it's going to be Cl minus. So Cl with a negative charge. I know that it's going to have a -1 oxidation number. And now, step 2, balance the atoms. Okay, I can see Cl2. That means that there's 2 chlorine atoms on the left, so there must also be 2 on the right. And guys, please don't fall into the habit of changing the small numbers. Guys, you cannot change the small numbers. The small numbers decide what the molecule is or what the ion is. All you can do to balance equations is by adding the big numbers, the coefficients. Now, what about the charges? Now, I gave you a little bit of a tip. To balance out negative charges, add electrons to the other side. So that's exactly what I'm going to do. So plus 2 electrons to balance out the 2 negative charges on the right. And there we've got our 2 half reactions. Okay, just to identify which one is which, I hope that you can see that sodium is undergoing some oxidation over there, and that chlorine is undergoing some reduction. Reduction because I can see the electrons on the left, oxidation because I can see electrons on the right. So I hope that you're working ahead of me and you managed to figure out what's going on in the next one. Okay, now here's an element that we don't often speak about, and this is strontium. Okay, it's a very, very strange element. You'll find it in group 2. Not many of you have dealt with it. The reason that I want you to play around with this is because strontium is in group 2. You can treat it like calcium or magnesium or barium or any of those. Strontium is very useful in sugar processing and inside fireworks. It makes a beautiful red color when I do redox on it. Now, strontium is a metal before the reaction. What happened to strontium after this reaction? I see that it's inside a compound. So let's once again color code these things. So let's actually tell the story of strontium in some blue. Let's keep this all separate. So strontium is going to be blue color. And let's see what happens to strontium. Okay, so strontium is a metal before. So we know that strontiums don't have a charge because they're elements. Now, after the reaction, it's inside a compound. Go and take a look at those 8 rules I gave you last week. Guys, strontium is going to change into a +2 oxidation state, or oxidation number. That means that it makes Sr2+. Okay? Now, I check to see that there's 1 strontium on the left, 1 strontium on the right. Everything looks good. Now what happens? Strontium, okay, strontium 2+, good. Let's balance out the electrons, balance out the positive charges with some electrons. Everything looks good, adds up to 0 on the left, adds up to 0 on the right. All the charges are balanced. Okay, now let's pay attention to some bromine. The reason I use orange is because bromine is kind of an orangey color. Okay, now bromine goes to become a bromide. So let's tell the story of bromine there. Okay, so bromine down at the bottom here. I've got Br2 because remember that Br2 is one of those diatomic elements. Now, diatomic is something I should only talk about when I talk about elements on their own. Okay, now Br2 changes into bromide ions. So step 1, tell the story. What did I have before? What did I have at the end? I had bromine, now I have bromide. Group 7 elements, also one of those rules that I gave you. Group 7 is going to make a -1 valency or a -1 oxidation number, and that's where I get Br minus. Step 2, let's balance out our atoms. There we go. I need 2 on either side, so I've balanced out my atoms. Now to balance out a negative charge on one side, I'm going to put electrons on the other side. How many? Well, there's 2 times Br minus. That means that I've got 2 electrons that I need to add. So things are getting a little bit cramped there. I hope you can see what I'm doing. So let's actually just move things across a little bit. There we go. Let's give a little bit of space for bromine. Okay, now this next one's going to be a real challenge. Guys, you've got to figure out the oxidation number over here. And I'm going to start off, but I'm going to leave a little bit of a challenge for you guys. Okay, now I've balanced out this reaction, but there's something missing. You'll notice that the oxygen is not quite balanced. And this is going to lead into our next part. There's something missing from the front of this oxygen, and that's a problem. We're going to solve it using half reactions. I'm going to show you an entirely different way to balance out chemical reactions, and this is really cool. If you balance out your half reactions, it'll actually balance your original reaction for you, and I'm going to show you how to do that in a moment. Okay, but let's tell the two different stories. Let's tell the story of iron. Okay, so Fe changes into Fe something on the inside of iron oxide. Now that's your first problem. I need to find out the oxidation number of iron which is inside this compound. So let's do a little bit of revision on how to assign my oxidation number before I let you get this challenge. Okay, how do I come up with the oxidation number for an entire compound? One of the rules from last week said that the oxidation numbers inside a compound all add up to 0. So let's make a simple sum. So 2 Fe, so 2 iron plus 3 of oxygen. Now oxygen we know now is -2. Because it's a molecule which is neutral, it's not actually a molecule, it's an ionic subunit, but don't worry too much about it. I know that the formula, or the formula unit, will add up to 0. Okay. Now I've got a simple algebraic sum. So I know that 2Fe minus 6, there we go. So minus 6 is equal to 0. If I take the 6 across and divide by 2, I'll find that Fe is positive 3. And that, guys, is a little bit of a clue as to how to go about these two half reactions. Guys, I want you to try tell the story of iron and oxygen while I'm on a break. And I'll give myself a little bit of breathing room, and I give you time to share on the page. Fantastic, guys.
All right. We are going to take a very short break, Mindsetters. Hit us up on the Facebook page with all your questions and your comments for Phil, and I'll see you straight after this. Welcome back, Mindsetters. From that break, I will not waste any time. I'll take it straight back to Phil.
Fantastic. Thanks so much, Lenny. Okay, guys, before we went away, I wanted to see if you could come up with the stories of iron and oxygen. Okay, now a lot of you are asking about the coefficients of the elements which are going into these, and you're saying, what happens to the coefficient? Do I just forget about them? Guys, they're going to make a comeback a little bit later on in the show, so don't panic about it. Let's tell the story of iron. Okay, so now before the break, we decided that iron as an element went into my reaction. When it came out in the form of Fe2O3. That meant that I had iron with a 3+ charge. So let's write this down. Let's tell the story of iron. So iron goes from Fe, and it changes into Fe3+. You might notice that I'm not putting a coefficient on this quite yet. Okay, so I know the story of iron. It changed from being neutral with a 0 charge to being iron with a 3 positive charge. Now, I need to check my elements. 1 iron atom in, 1 iron atom out. Now, what about the electrons? There we go. 3 electrons come out. Okay, so I know that iron is undergoing oxidation. And in fact, the oxidation of iron is called rusting. So if anyone has ever seen rust, and that's all of you guys, if you've ever seen something which has been left outside and it goes that orange color, that orange color is iron 3+. In fact, you have seen iron 3+, and you depend on it every day of your life. Guys, the iron inside my bloodstream is in the form of iron 3+, and that's where blood gets its red color from. It's a protein, and it's this complex protein, and what happens is this protein contains iron 3+, and that gives it a lot of its color. Okay, fantastic. Now we've told the story of iron, and we've told you about blood as well. Now let's talk about oxygen. Oxygen had a different story. Oxygen started as O2. O2 changed into oxide ions, which we now know are always double negative. The way that we balance out double negatives, but only once we've checked out our atoms, guys. 2 oxygen atoms in, 2 oxygen atoms out. Now let's balance the negatives by putting electrons on the left-hand side. How many? Guys, most of you are going to say 2, but it's not. It's 4 electrons. The reason that it's 4 electrons is because there's actually 2 times 2 negatives. So there's 4 negatives on the right-hand side. Now, here's the question you should be asking yourself. How can one of these reactions supply, and this is a reaction which gives away its electrons, give away 3, but this reaction over here oh, wait a minute, this reaction needs 4 electrons. Something's not right, guys. Something is not right, and this is where we start to get the coefficients from. Guys, we're going to come back to this one if we have a little bit of time, but I want you to think about this. How is it possible for one reaction only to give 3, but the other one needs 4? And the answer is that can't happen, guys. You can't just invent electrons or have extra electrons lying around. Guys, I've got to have the same amount of electrons in both of these reactions, and that's where you're going to get your coefficients from. Okay, so now what I'm going to do is I'm going to show you how to work with your half reactions. Can we add them back together to give a full reaction? So the name of this reaction is called a net-ionic reaction. And I'm going to show you how to make one of your own. Okay, so each one of these are only half the story. We can combine them again. Okay, so now let's take a look at our original reaction here. We talked about Mg. We saw the oxidation half reaction. Magnesium changes into magnesium 2 plus 2 electrons. I see oxygen. I add 4 electrons and it becomes 2 oxide ions. But this is not the whole story, guys. Here's the problem with writing them out next to each other. And I want you to write them above each other. Magnesium is only giving out 2 electrons, but oxygen needs 4 for its half reaction. So what I've got to do is I've got to make the electrons equal. I've got to balance my electrons. So here we go. So when I balance out the electrons, you can see that I've multiplied, and guys, here's where the coefficients come in. All I need to do is to multiply everything in the top reaction by 2. So I multiplied everything by 2. And why did I do that? There we go. 4 electrons out, 4 electrons in. And that's what I'm looking for. The 2 reactions must have the same amount of electrons. Because I can't just give away 4 and only 2 arrive in the other reaction. They must have the same amount of electrons. Guys, it's all about balancing the electrons. Now, the only thing that remains is to write those 2 reactions, instead of as halves, back into a whole reaction. And let's just see what that all looks like. Okay, so now you might say, well, Phil, that doesn't look very much like my original reaction. Okay, so let's just tick it off, and let's see what goes on here. I can see that I've got 2 Mg. There we go, 2 Mg. There's 2 Mg. There's O2. There's O2. So now I've written everything on the left-hand side all together. But you might say, where are the electrons? Now this is like a maths equation where I've got 4 electrons in, 4 electrons out. Guys, they cancel out. When I've got 4 electrons going in and 4 electrons coming out, there's no use in having them both on either side of the equation. You can cancel them out. Okay, so that answers the question of what happened to the electrons. But what is this whole business happening on the right-hand side? I've got 2 Mg2 plus 2 O2 minus. If you think about this carefully, guys, what I've actually shown you here is a recipe for making 2 magnesium oxides. But now you don't have to combine them because this is called the net-ionic reaction. Net-ionic means net is the sum, the addition of everything, and ionic, we're just showing what ions came out. I have indeed actually gone from 2 Mg plus O2 to make my product of 2 MgO. That is my original reaction. And guys, take a look. The coefficients are back because I balanced the electrons. And this is actually a very reliable way of making sure that our reactions come out balanced. But it's a very long process if that's the way that you want to balance your chemical reaction. But the reaction actually balances itself as long as you look after those electrons. Now, as with anything, the best way of seeing if we understand it is through a couple of questions here. So question 2 for this evening is we're going to start combining these half reactions. We're going to start seeing what comes out of these half reactions. And we're going to try and see if we really understand how to glue 2 reactions back together and see if we can get a net-ionic reaction. Okay, so let's start out with the first one. I particularly like this one because this one makes table salt, and I'm a big fan of salt. Okay, so here we go. Sodium goes to sodium plus an electron. Now, do I know if this is oxidation or reduction? Well, guys, let's do a little bit of investigating. Electrons are on the right. It means that electrons came out. Oh, wait a minute. Electrons coming out. That means there's loss happening. So loss of electrons, this is oxidation. That's my oxidation half reaction. What about this next one? Chlorine plus 2 electrons. Oh, chlorine plus electrons. That means that chlorine and electrons went into the reaction. The electrons on the left-hand side, that means that I've got reduction. But that's not what we came here for. Guys, what I said is that we have got to put these together into a net-ionic reaction. And let's do that in green. Okay. So sodium plus goes to sodium plus an electron. So 1 electron is going to be coming out of this one. But now here's the problem. Chlorine needs 2 electrons. So how do we solve this problem? Well, what you do to balance out electrons is the same as the way that you find common denominators inside maths. Find your lowest common multiple. Your lowest common multiple of 1 and 2 is 2 itself. So I can make both of these reactions have 2 electrons. But remember that you have to multiply everything in my reaction by 2. So I've got to have 2 Na, goes to 2 Na plus 2 electrons. And that means that my 2 electrons will cancel out. Now, what I've got to do is write everything on the left together, everything on the right together without the electrons. So let's do this together. So 2 sodium atoms will combine with 1 chlorine molecule, and the product, the net ions, which will come out of this, are 2 sodium ions, those delicious sodium ions, plus some chloride ions. There we go, and there's 2 of them. Notice how the coefficient has come back. Okay, on to the next one. This next one we've done together. I'm going to see if you were listening a little bit earlier. This is the burning of magnesium and oxygen. Okay, quickly identifying oxidation and reduction. Magnesium was undergoing oxidation. How do I see that? Electrons on the right. Electrons are leaving the reaction. They're coming out. There we go. So that's oxidation half reaction. Next one has got to be the reduction half reaction. Why? Because the electrons are on the left-hand side. Okay, so let's do some balancing. Let's switch colors again. How do I balance out 2 and 4? How do I make 2 and 4 exactly the same number? Well, guys, if you've been listening to anything that I've said, you've got to make sure that your electrons are the same number. How do you make 2 and 4 the same number? Why don't we make them both 4? So how do I make this into 4 electrons? I need to double everything. I need to multiply everything by 2. And guys, I know a lot of you just write a multiply by 2 in the front, but I've noticed that a lot of my matrics, a lot of my grade 11s forget to multiply one of them. So I actually want you to go through each half reaction and change all the numbers. Change the number in front of the Mg, change the number in front of Mg2 plus, and change the number in front of the electrons. And here's why I'm doing it. I can cancel out the electrons. There's got to be the same number of electrons going out and in. If that's not the case, you cannot cancel it out. Okay, so magnesium is one of my reactants. Let's write out all the reactants together. So 2. Now let's just give myself a little bit of space so I'm not bending over. There we go. So Mg, there's 2 of those atoms. What else needs to go on the left-hand side? What about the oxygen? There we go. So oxygen is also on the left-hand side. Don't write in the electrons. You don't have to. What's on the right-hand side of both those arrows? I see 2 magnesium ions. There we go. So 2 magnesium ions and 2 oxide ions. Really, really nice. Now, for the last one of these types, what I'm going to do is I'm going to make a very unusual compound. This is called aluminum sulfide. Okay, now sulfides are not compounds that most people deal with. They kind of smell really weird. All that you would need to make one is the metal and the non-metal inside there. So for instance, if you wanted to make zinc sulfide, you would take zinc and sulfur and put them together. So aluminium and sulfur combined will give me aluminium sulfide. But now let's look at those half reactions together. Okay, so aluminium is undergoing oxidation. Once again, metals will undergo oxidation generally from element through to ion. So aluminium lost 3 electrons, okay, and 3 electrons come out, and that was definitely oxidation that was occurring over there. So aluminium underwent oxidation. What did the oxidizing? Sulfur did the oxidizing. So sulfur, to do the oxidizing, underwent reduction itself. So it underwent reduction itself because of those electrons over there. So there's reduction happening over there because sulfur is gaining those electrons, sulfur is taking in those electrons. Now we've got a slightly different problem to the one that we had earlier on in the show. How do you make 3 and 2 into the same number? Now it's not quite as easy as examples A and B. What I've got to do is I've now got to get them to the lowest number that they both go into, and that is 6. So I need to find a way to make both of these equal 6. I need to make 6 electrons and 6 electrons. How do I do that? Well, this top one, to make 3 into 6, I needed to multiply everything by 2. By 2. Notice how I'm changing all the numbers as I go through. How did I change 2 into 6 in the sulfur equation? I needed to multiply by 3 in both cases. So that's really important. Notice how by balancing the electrons, we balance out the equation. And once you've balanced out these electrons, you can cancel them out. And that's the beauty of this. This tells me that 2 aluminium atoms plus 3 sulfur atoms will go together to give me some ions. Which ions? They're going to give me 2 aluminium, 3 plus ions, and 3 sulfur, 2 minus ions. And that's the beauty of this. I see that aluminium and sulfur is going to give me aluminium and sulfide ions. And this is the way that you do this. Guys, you don't have to worry about the coefficients. If you follow the steps, you will actually get the right coefficients. Luni, how's the page looking? It's busy. I can see she's typing away and answering all of your guys' questions. One of the things that I wanted to point out while Luni finds your questions is that I want to make sure that you guys are following the correct steps. So when you write these 2 half reactions, I want to see that you balance your electrons, you change all those numbers. Don't forget everything. And if you have to, I want to make sure that you write down everything on the left-hand side. So even circle them or highlight them if you have to. And I want to see if you guys have got any questions. It looks like Luni's been answering some questions there.
Those are general questions.
Oh, okay, fantastic. Okay, well, guys,
Okay.
yeah.
I have a question from Vincent. He's asking, there are 2 types of ions, Fe2 and Fe3. How do you differentiate them?
Oh, very nice question. Okay, Fe2 and Fe3. Okay, now, if you've taken a look at some of the notes that I gave you guys, you'll notice there's some questions about iron 3 oxide and iron 2 oxide. So we're going to deal with those quickly before we end off the show. So I just want to differentiate between iron 2. And for those of you that have said, like, oxidation numbers, those scare me. If you've ever seen something that looks like this, you've actually been dealing with oxidation numbers all the time. That says iron with an oxidation number of 2. It doesn't mean that I have 2 ions. That is the oxidation number of iron. So iron 2 oxide and iron 3 oxide are entirely different. Okay, now here's one of the secrets, guys. Iron 2 oxide has got a darker, greener, bluer color. Now, this is one of the really strange things. I love biology because it's one of the subjects I had a big passion for. You'll notice that there's actually 2 colors of blood-containing vessels inside your arm. One of the reasons for that, now this is not the full story and this is a big simplification, is that iron 3 has got a more reddish color, while iron 2 has got a slightly more blue color. And this is one of the reasons. What happens is when hemoglobin, that protein inside your blood that carries all that oxygen, lets go of its oxygen, it turns back into iron 2, and it changes its color from being quite so red. So when your blood starts running out of oxygen, you'll notice some people's lips get blue. Okay, that's a bad sign, guys. That means that there's too much iron 2. Your body needs iron 3. Okay, now let's differentiate this. Iron 2 oxide means that iron has got a 2 plus, or a positive 2 oxidation state. So this has got a positive 2 oxidation number. This has got a positive 3 oxidation number. Now what does that mean for the ion? Iron 2 means that it's Fe2 plus. Iron 3 means that it's Fe3 plus. Okay, so I hope that answers the question, what's the difference between these two? Now, the differences will also extend to the formulas because oxide, remember, is negative 2. This oxide is also negative 2. So how do we combine Fe2 plus and O2 minus? The formula that I'll make there is FeO. Now that's called magnetite. It's a black mineral. It's dark in color. What about Fe3 plus and O with a 2 minus? If I combine these two, I get Fe2O3. Guys, this is a formula for hematite, and hematite is actually rust. It's got this orange color, and this is one of the reasons that you actually get orange in the dirt outside. One of the reasons is that because it's got a lot of oxidized hematite, and hematite actually gives us this beautiful Fe2O3. And I hope that answers the question between iron 2 and iron 3 and talks about the different colors inside your blood. Hope that answers that question.
Thank you so much, Phil. Mindsetters, thank you so much for tuning in. Thank you for your questions. Remember, if you did not get to all your questions, we do have a help desk and an app on our Facebook page, so check it out. I did post the link. Otherwise, see you next week from 6 till 7. Until then, we love you and goodbye.